Hi students. So today we start lecture 39 in our aerospace engineering course, and today I'm going to discuss about the range of propeller powered aircraft. So essentially in a previous video we talked about the endurance and range as general concepts for aircraft which are typically jet aircraft or propeller aircraft, and now we are going to derive closed form equations for each of these cases. So today we are going to look at the closed form equation for range of a propeller powered aircraft. I am Dr. Ranjan Ganguly. So now these formulas are also known as the Breguet formulas for steady level flight. So it's important to remember that these equations are valid for steady level flight, which effectively means that your lift is balanced by the weight and your thrust is balanced by the drag. So in this situation, what happens is that the pilot would create a state such that the available power is equal to the required power, and in this case both PA and PR is equal to D into V infinity. So that's the total drag into the velocity. So this is the force into velocity concept which essentially leads to power here. So what happens is that when you have a typical propeller engine, the available power is some value eta times the power, which is the brake power output of the engine. So unfortunately, all this power, which is P, does not get transmitted to the PA. So there is some loss here. So essentially, this is an efficiency, and this may be something like zero point 0.9 or below. So we can write P as PA divided by eta, which becomes dV infinity divided by eta. So remember, again we are in steady level flight, so thrust is equal to drag and lift is equal to weight, and we are dealing with the propeller aircraft. So we are going to just recapitulate some of the concepts about weight we discussed before, because we are going to use these concepts again. So remember that W0 is the gross weight of the airplane. So that's the starting weight of the airplane. So if you are starting at some point A, this is the weight of the entire body as well as the fuel. So essentially here you assume that the airplane is completely filled with fuel at this point, and W1 is the weight of the airplane without fuel. So that's the weight at the point B. So essentially the aircraft is flying from point A to point B. So its weight reduces from W0 to W1. So keep in mind that W1 is W0 minus WF, where WF is the weight of the fuel which is there in the aircraft. Also remember that W0 is of course greater than W1, because when you start the journey your aircraft is full of fuel, and when you end the journey that has been essentially expended in the journey here, and we are talking of this distance A to B as the range. So this is given by the letter S. So now we are going to combine all these equations together. So let's start with the fact that the power P equals PA by eta, which is dV infinity by eta. And next we use the range expression I derived in the previous lecture, which was the general equation in terms of the integral. So the integral is from weight W1 to W0, V infinity dW by Cp. And so we put in the value P here. So what happens is that I get the dV infinity term here, and the eta term goes up in the numerator. So this is the equation we obtain here, and then there is some cancellations as far as these two V infinities are concerned, and so I get this equation here, which is eta dW and CD. Now let's again continue to further simplify this equation. So what I can do is I can write this as eta CD W by W. So essentially nothing stopping me from writing W by W, because both these are same and so they would get cancelled. And then I use the fact that we are in steady level flight, therefore the weight here is equal to the lift. So I can bring this L here, and then I can take the second W and I can bring it below the dW term. So this is the use of the fact that we are essentially assuming steady level flight here, and we are assuming the fact that lift is equal to weight. Now, once we do this, the point here is that we can express this integral in terms of L by D, and this is something we are very familiar with as far as aerospace is concerned, because we are always concerned with the lift to drag ratio. And now we also obtain dW by W, which lets us actually calculate this integral. So we write the expression for range once again, and now you clearly know from calculus that this is something we can integrate, provided we take out some of these remaining terms outside the integral sign, because we need to essentially just focus on the dw by w term. So now we are going to assume that L by D or CL by CD, C and eta, they are all constant throughout the flights. And so this is quite a legitimate approximation which we are making. Of course, there may be some variation in these, but generally what happens is that it's not very much. And so what happens with these formulas which I am getting today is that they are accurate to about 10 to 20% in comparison to actually doing the integral using numerical means or using computer programs. So now we can get the closed form solution here. We bring out the eta by C term, we bring out the L by D term. So L by D becomes equal to CL by CD here. And so I get the term log W0 by W1. So remember from calculus, the integral of dw by w is ln, which is the natural log to the base e. And so W0 and W1 comes because I have the definite integral here. So this is one place where calculus is becoming handy. So let's now write down this formula and try to extract some design information or some aircraft information from here. So we can clearly see that we would like to maximize range. That's something we would like to do, because on a particular tank of fuel you would like to travel as long as possible. So some of the things you can do here are increase the value of terms such as eta, which is the efficiency of the propeller system. Try to make C as low as possible, so that is the specific fuel consumption. So essentially the engine should be as efficient as possible. The CL by CD should be as high as possible. So again, this is something which is coming from the drag polar and the airplane design and the aerodynamics of the airplane. And then we are going to look at this part in the next slide, the log W0 by W1 part. And to remember, this equation is for a propeller airplane. So let's now look at this term here, which is the log term. Now, to think about this term, we immediately realize that W0 by W1 should be as high as possible. And this happens because we clearly see that W0 is greater than W1, because you start with a greater weight and you end with a lower weight during the flight because the fuel weight is lost. So W0 by W1 is greater than 1 if I were to divide these two. So what happens is that this value W0 by W1 is going to be greater than 1. And suppose I plot it here, I have plotted these cases of W0 by W1 is greater than 1. And on this axis, I have plotted log W0 by W1. So this is log to the base E. Now, you can very easily do this plot in an Excel spreadsheet, and what you're going to get is a line like this. So this clearly tells you that this is directly proportional to W0 by W1, and so you want to maximize this value of W0 by W1. Now, to maximize this value, you will immediately see that you should have higher values of WF. So essentially, highest fuel weight is the best as much as you can carry as far as the aircraft design process is concerned. So again, that is something which comes out of common sense also, but that's something which the math is also telling you. So in any case of any equation or closed form solution, it's always a good idea to verify your equations with your common sense thinking. So let's summarize this lecture today. The lecture today, we started with the expression for range, which I derived in the previous class, which was very general and expressed in terms of an integral. and I expressed it in terms of the closed form solution, also known as the Breguet's formulas. So here we clearly saw that this was dependent on certain factors such as eta, which is the efficiency of the propeller, the specific fuel consumption C, the CL by CD ratio, which should be maximized, and also log of W0 by W1, where W0 is the starting weight or the gross weight of the aircraft when you leave the airport, and W1 is the weight of the aircraft when you land at the new airport. So essentially, one of the main problems for aircraft is that you often want to design an aircraft to maximize range. So if you are somebody who is given a task of designing an aircraft which flies between two very distant places, then this is the equation you are going to think about how to maximize the value of R. So for example, nowadays there are aircraft which can fly, for example, from San Francisco to Bangalore, and in such cases the range maximization becomes the main problem. So today's lecture we saw that if we use the integral definition which we discussed before and we use certain approximations in terms of steady level flight, then we can obtain an approximate formula for range. Of course, you need to remember that this formula is only valid for steady level flight, whereas the previous equation or the equation which used the integral was valid for situations which included takeoff, climb, landing, and so on, whereas this equation is only valid in the cruise region. So like I mentioned before, it would be something like 10 to 20% off from the exact solution. So you would have to exclude the parts which involve takeoff and landing and so on. But it does capture many things, and it also gives you a physical feel about what are the important things you need to consider if you want to design an aircraft for maximization of range. So I'll stop this video here, and I will see you in the lecture on endurance in the next class. See you then.